All right, so now after that you have already learned carefully and be aware, fully aware that what a function is and that a function has a graph representation, as well as at this point knowing how to operate with a function. Then now it's time to learn in detail about the domain and range of a function. Now, for some instructors, for some math professors, they teach this as a part of the lesson where they're teaching about function, but I decide to teach this as a separate topic right here because it deserves all of our attention here, because it has all that in-depth detail. And so here I highly recommend this lesson is to be viewed when you are at a pre-calculus level right here. This lesson is aimed at audience who are in pre-calculus or college algebra course level. Okay, and as the title is saying, so needless to say, this lesson must be learned after you have already learned about what a function is and at least how to operate with a function. But and also highly recommended to be the view after you have learned that after you have learned the kind of basics that any function has a graphical representation, because a lot of the explanation here, a lot of the explanations here will be delivered through graphical interpretations as well. Okay, and so let's now go ahead and dive in for this. All right, so now I'm going to erase the subject title, the topic discussion title right here. So now, when I was introducing about function in the earlier video lecture, I was talking about a few functions as following. Let's now start out with giving a function in functional notation. F of x equals square root of x. Okay, so with a function like this, so at this point, would any assumingly that allow me to assume that anyone has already understood what a function is and what it does to you and what you can do, what you can operate with a notation given like this. And so now the x is the input. Okay, so we have seen this similar kind of example in earlier lectures when I was introducing about function. So when we give the input value, or when we give 1 for the input variable, this function is going to evaluate, is going to process this input as the square root of 1. And then the mathematical operation here takes square root of 1 and gives us the answer 1 right here, and we have an output. So now I have to emphasize that again, this is input and this is output. Okay, but then I still remember clearly when I introduced this problem earlier, and you should have seen this if you've watched, if you've studied, and not only with me, if you study this the idea about function with any professors, with any instructor right here, right at right at the moment when you were introduced to the idea of function, you should have seen a problem like this once or twice before. But on the same function here, this is what I mean on the same function. What about we're going to give an input -1? Because so far throughout our understanding, then it seems like any input is going to work. Okay, because simply for a function, it's just going to take an input. It's a rule. It processes the output and processes the input and give out the output. So a function is a rule that takes an input to an output, right? And with the condition, with that requirement that every input goes to exactly 1 and only 1. Okay, but in the end, we still maybe at the end of the discussion of the thorough discussion about what a function is, anyone learning about function is still under the impression that any input is going to work. Any input is going to work. Then let's find out. And so now back to what I was in the middle of saying. So we tried with input x equals 1 for this particular function, and it came out successful. We had a value. So successful means the function could proceed to the end. This function we were able to proceed to the end. But what about when we change now to a different input, f of -1? Let's see what's going to happen. So in the way how it is at this point, with this input being now given as -1, I'm going to take that into the square root operation, because that's the rule for this function. The rule says we take square root of the input. And so now we take square root of a -1. But now, and as I've said quite a few times in earlier video lecture, and then any professors who are teaching college algebra or pre-calculus, of course, we also indicate clearly that when we're at this level of math, we're staying in the real numbers, okay? And so within the real numbers, there is no defined output for this. There's no defined answer for this. Or in other words, simply putting it, we just can't calculate square root of a negative number. Square root cannot be we cannot evaluate the square root of a negative. This is square root of negative 1. And so back in the earlier examples, back in the earlier lessons, when I introduced a problem like this, I used a term, and it's still the same term. This answer is undefined. Okay, so now it's time to sit back and look a little bit. So wait a minute, because I just now pointed out that kind of situation right there. So we're gonna start thinking a little further in details. So wait a minute, some inputs worked, and works means we had a value. And by the way, in that case, when we successfully came out with a value through the rule of the function, then we say yes, the function is defined. Okay, the function is defined at this input, because we can have a value successfully. We can have a value successfully obtained. Okay, as for the output, but then at this input right here, we were unsuccessful. We were not successful to get an output, and that's why I left the answer here as an undefined. Okay, same function. Let's try again. So, or maybe let me switch to the other board to maximum so that I can still keep the other board for a good purpose. So what about f of 5? Okay, so with this input right here, we have a square root according to the rule of the function, and f is still that f of x equals square root of x generally. And so f of 5 now means the input is switched to the value 5 for the input. So we take, that means the rule says we take square root of 5. Now I'm not saying that it's a nice looking number at the end, but we will have an output. This is our output. Okay, square root of 5 is a value roughly above 2. It's not even 3, but it's roughly above 2 right here. Okay, so if we have to put it in decimal, it's a 2 point something, roughly above 2, as I said. But in the end, this is a defined value. So with this input 5, even though the answer is not a nice looking expression, not a nice looking value, but it's a number. Okay, it's defined. But now f of negative 4, okay, equals, well, the rule says we take the square root of the number negative 4. But this is where problems comes in again, that we cannot take square root of a negative. Okay, so in other words, in our understanding at this point, this value, this operation gives an undefined value. We have an undefined value. Okay, and now we can try with f of 0. Okay, so now this value right here, now 0 is the input. Okay, and the rule of the function says we take the square root of the input. Okay, and then square root of 0 is entirely possible. And I'm now starting to use that term right there. The square root is a mathematical operation. So taking square root on 5 is possible. That's why overall here it's a defined value. Taking square root of a negative 4, or hopefully anyone watching this is going to start having a generality. Taking square root of a negative number is impossible. And that's why we had an undefined. And now taking square root of a 0, okay, is possible. Okay, square root of 0 is 0. Okay, and so now we start formulating for ourselves, we start generalizing for ourselves an idea as following. For some function, like say for example, this function that we're particularly working with, this function does not take all inputs out values out there. Okay, technically, for a function like this, then we're gonna give the numerical inputs, but this function, in the way how it was written, in the way how it was defined, in the way how this function was let it be, okay, then it takes only positive value. And also, you see positive 1 for input, it worked, it gave a defined value. It took positive 5 as input, it worked. It took even 0, it worked. Okay, so this was defined. All right, but when it hits to a negative value as an input, it gave us an undefined. And then was that true? Was that also true for this -1? Yes, when the input was -1, it came to an undefined. And so now back to what I was in the middle of saying, this function does not take any inputs. It's not going to like easily take any numerical inputs for that. There's a certain restriction, okay? There's a certain restriction of the inputs. There's a certain requirements of the inputs that makes the output work, that makes the functions work to give a successful output. Otherwise, outside of that zone, okay, outside of that zone of the required inputs, then it's not going to work. Like say, see, -1 here is outside some kind of zone right here. All right, so that's the idea that I'm leading anyone watching this video into. Yeah. So the idea now is that it's just the way it is for functions. Some function, the way how we wrote the function, the way how we create the function, how we define the function ultimately, then it's gonna the function itself is gonna have a certain restriction, a certain requirements that restricts the kind of inputs. Okay, so here for this function, it looks like, now I'm gonna clear out the board. Okay, so I'm gonna clear out the board and I'm gonna say for this function, okay, I'm gonna use the term only possible. Okay, this function is only possible to take. Okay, so this function is only possible to take inputs, the kind of inputs x positive, yes, all right, that's what it is, but then also equals 0. So any value that we've investigated, any value greater than 0 or equal to 0, a function like this function, and I'm not going to make any generalities about the kind of function. I'm just saying that, well, once you're specifically looking at this function right now, okay, the point now is that there's only a certain zone of values that's possible for the function to take, and then outside of that, it's not going to work. Okay, all right. So in that way, right there. And in that way, now let me briefly bring back another problem right there. Very early, much earlier now, particularly or specifically for anyone who has been studying with me, then right from my beginning lectures right here, when I start introducing the idea of a function, I brought in the example of being a vending machine. Okay, and let's enforce that idea again, because the idea I'm pointing out right now is that for some function, the way how it's written, the way how it's designed, the way how it's defined right there, then it's not the way how it is. It's not going to take all kinds or any kinds of inputs. There's a certain restriction to the inputs, the kinds of inputs being given to it. Okay, so like earlier I gave that the f of x equals square root of x, and I ultimately made that note. That function was particularly only possible to take the inputs being greater than or equal to 0 numerically. Okay, so let's look at that vending machines again. I brought this example in my very beginning lecture when I first introduced about function, and here we can have a look at that again. Now, as far as the pricing or money, and then this is products. Okay, then the vending machine, if we give it, the vending machine sells the products to us. So if we're inputting $1, okay, if we're inputting $1 for the price, so this is inputs going in this way. Okay, this example is supposedly user friendly right here, because a lot of people know about what a vending machine is. Okay, so when you're inputting a price being $1, then you're looking at you're getting out, the machine is giving out a soda can for you. Okay, and then when you're giving the machine 75 cents, the machine is giving you a water bottle. Okay, and I mean, actually I'm looking back at my old note, and this was supposed to be a snack. All right. And then if you're giving it $1.25 here. You're looking at a coffee bottle, like a Starbucks bottle, okay? And then if we're giving it only 50 cents, okay, it's giving you a water bottle, okay? All right, and then this has no, this machine goes with exact change only. Okay. So this is what it means right here. See, in the way how the function, it gives an input, and any one of these products here comes out as an output. Okay, so we were so clear at that point. Now up to this point, looking back at this example, okay, and so now let's look for what's possible for this machine to take, and what's impossible, and what's not possible for this machine to take. Because, like I said, the idea I start introducing anyone into is that some function, the way how the function is designed, the way how the function is defined like that, right? Then it, you know, some input is possible for the function to take, and some other input is impossible for the function to take. Okay, so let's find out and pay attention to this rule that exact change only. It's just the way how this machine is given. Okay, so if you're giving like x equals 2, meaning if you're providing a pricing being exactly $2, this machine does not give exact change, so it won't know it. So in other words, this is impossible. Okay, this is impossible for the machine to take right here. Whereas if you're giving, and so I call this, so the impossible is just more like a common daily term right here. But now, mathematically speaking, if we're giving, I also remember that I refer to this machine, this function here. Once we agree that this was a function, then we call it the VM of P. Okay, it's a function that takes inputs P. And so in this case, VM of 2, okay, is undefined. Okay, so how do I know it's undefined? Because you see, first of all, the machine itself does not takes only exact change. So if you're giving a $2, do we have a price? Think about whether or not we're having a price that a product that matches with this price. We don't, and that's where it says undefined. If you're giving $2 for this machine, well, if someone is not happy about this machine in the way how it's designed, then maybe you can raise that concern to the manufacturer who created the machine. Okay, but the idea now is once it's already created and functioning as a machine like that, all right, and be a function on its own, then it does not have a definition for input 2. So when you're providing a $2, this machine does not know what to do. Okay, whereas if you are giving, let's look at $1.75. Now this is entirely possible. Okay, with this money, with this change that you're giving to the machine, because VM of 1.75 is indeed equal. It gives out now 1.70. Actually, I meant to write 1.25 right here. 1.25. So, sorry about the little error right there. But so otherwise, if it was 1.75 earlier, then that was another undefined. But now 1.25 is possible. Now, what do I mean? What did I mean by P equals 1.25 is possible? Because now for this machine, it will understand what to do when you're giving it $1.25. Because now when you're giving an inexact change again, of course. Okay, so when you're giving it $1.25, the machine is going to follow its rule and give out a coffee bottle. Okay, so VM as a function of 1.25 as the input is going to give us a coffee bottle. That's the output. All right, and this is where I say we had a value defined. Okay, it's defined, it has a product, and it was possible for this input. Okay, all right, so now I once again, with this second quick little example, I really emphasize the understanding that, and I hope I emphasized enough, the understanding that after the function is already defined, okay, there's a certain restriction about what inputs the function can take. Okay, some inputs are possible for the function to take, and some other inputs are impossible for the function to take. Okay, all right, so now I used this term, the zone, earlier. That was not a formal term, but it brings up the similar idea. So there's a certain zone of inputs where it's possible for the function to take, and outside of that zone of the inputs, then those are impossible. Those inputs outside of the possible inputs, those outside of that zone right there, those are impossible for the function to take. Okay, so there's a possible inputs and there's the impossible inputs. Okay, so now we come to that zone of the possible inputs. Okay, now is understood as the domain of a function, And so now I really like the wording of this definition I found throughout the many textbooks out there on the market. So I came to this textbook where it has the following the way of explaining, of wording the domain definition, or the definition of a domain right here. So allow me to write this down. And all right, so now we define what a domain is. So just that zone, keep that zone in mind right there. Okay, so now in formal term, it's a set. So the domain of a function, for short, just domain. Okay, because almost only when you're working with a function and you hear the term domain. Okay, so the domains is the domain of a function, of course, is the set of the author of this textbook that I'm using. Use that term where I also used in my explanation. It's a set of possible input values. Okay, set of possible input values. Okay, to a function. All right. So that's this definition that I found from a textbook that that's being used in some of the schools, the colleges I've been teaching. Right. The author of that textbook gave this definition right here. This style of wording of the definition. So the domain is the set of possible input values. So now at this point you now have a clear understanding of what it means. Because for example, when it was f of x equals square root of x, okay, then the set of possible inputs. I wrote that down in words earlier. This function, right, is only able or is only possible to take. For this function is only, okay, for this function it is only possible, right? That's that term possible. See, the set of possible inputs, only possible to take input values namely x greater than or equal to 0. See, think about this, x greater than or equal to 0. For this particular function, for this specific function, the line of numbers is here. Okay, 0 is somewhere on that line of numbers. Okay, and then this is the line of all the x values, for example. So the line of numbers is there. What we noted earlier is that for this function, it is only possible to take input values greater than or equal to 0. So if you're looking at all of the input values on a line of numbers like what I'm about to do here, then see, anywhere to the right hand side, that's greater than. And the skill that you're looking at an inequality and be able to translate that into a graphical shading like this, you should have learned that in a course as a prerequisite of this course we're currently learning. Okay, so greater than is shaded to the right hand side and also includes 0. So we're also accept that point x equals 0. Or in these modern day, quite a few textbooks use the interval notation like this. So it's a brackets pointing into the region right there. So this is the zone that I was talking about. Now the textbook is using, it's a set. It's a set of possible inputs. So all the possible inputs on this line stays to the right hand side of 0 and includes 0. That's why there's that brackets there. Okay, And so now that's the explanation of this domain right here, what it is, and here's the formal definition of that. And then I have to clarify a little bit too that it says, so it's a set, okay, possible inputs, values to a function. See, because any input is to be given to a function. And that's why the author of this textbook was stating in that way, the set of possible input values to a function. What is that? That is called a domain. So now this is the picture of the domain. This is the domain for this function. This is the domain for this function. Okay? All right, and so now you saw back to that function that I was here, it's just the logical reasoning. Okay, now after clearly understanding, it's now time to just have a clear way how to indicate, how to express what that domain is. Now we knew, I just now erased the logical interpretation of the domain here, the logical reasoning of the domain. And now we put that in a graph, okay, with shading and brackets and all that fancy understanding that you have learned. But now, you know, and I'm using that term fancy because, you know, it has a lot of details, okay? But now those kind of details are extremely useful because now looking at that, at all of that details, now the domain, okay, as an answer over here. Because sooner or later you will be doing a lot of problems where a function is given and you will have to be able to identify the domain of that function. Okay, so on standard, when you are expressing the domain of a function, of any function, okay, then the domain is expressed. Now this graphical is only for the scratch work, okay, and it doesn't hurt to show that on your formal work, but then as a final answer, almost in these days, almost 90% of professors, or even more than 90%, over 90% of professors do not accept this graphical shading of the domain, but they want, including me, we want the domain to be expressed in interval notations. Okay, so now, but then once you've had the graph done successfully, having the interval notation coming down is easy. Okay, brackets, okay, 0 is the end on that bracket side. There's no right side that ends the shading right here. So we're going to say 0, comma, positive infinity. Now, anyone learning in this video lesson is surely comfortable enough with this infinity symbol right here. It just means we're not going to have a stop here. We're going to just keep shading further and further out. But this is for this particular function, f of x equals square root of x, we found the domain of this function is anywhere from 0 to infinity. Okay, anywhere from 0 to positive infinity, to be precise. Okay, so that's the domain for this function right here. And it wasn't even a formal example. It's just something I brought up to point out that the idea about the domain exists for any function. Okay, any function, as long as once you have had the function defined, there will be a domain. Okay. And so it's, in some problems you have to look for domain, in some other problems you don't have to look for a domain, but you always have to be aware that there will be a domain. Okay, for any function, there will be a domain. Okay, so now in that way, what about that vending machine that I brought up earlier? And I erased the picture right there. Okay, so let's look over at this board. All right, so for our vending machine, we're looking at, so pricing allowed me to this time put the price on the left-hand side column, and then the product comes out on the right-hand side. And this is the vending machine. Okay, so giving it $1. All right, we're getting a soda can. Okay, and getting only a point, giving it only a 0.75. We're looking at a snack. Okay, and only a 50 cents, only a 0.50 of $1. Then we get a water bottle. All right, and when it comes to when we're giving it $1.25, well, the machine comes out for us a coffee bottle. All right, so coffee bottle and all that, and again, it's exact change only. Okay, exact change only. So that's the rule of the function. Okay, so in that way, I already pointed out when I was introducing about domain, this function, once it's defined, after we've had the function defined and given to us to work with, okay, this function takes only, I talked about vending machine VM of 2.00. This was impossible. Okay, that was the term I used back then. But now, clearly speaking, that's another way of saying, formally, we're saying undefined, because the rule of this function did not define what to do. The engineer who designed, whoever the engineer that designed this machine did not tell the machine what to do when user would give it $2. Okay, and so that's why it's undefined. And according to the rule here, exact change only. So the function will not know to give change back. Okay, and so that's one way. So this input is outside of the domain. So now, what inputs are possible? $1 is possible. 75 cents is possible. 50 cents is possible, or $1.25. Only those four limited values. Only those values. And yes, so in that way, the domain is a set of possible input values to a function. Okay, then in this case right here, now here is a slightly different situation or a slightly different place where we cannot use, it's just the way it is, we cannot use the interval notation here because these are discrete input values right here. So very commonly, anytime that your function is given and represented as a table like this, okay, then we have to express the domain in set notation. So the domain here is a set. So this is the standard set notation. Okay, an interval notation. An interval is also a set, but a set of infinitely many values. That's why we have an interval of numerical values. But here we only have a few, about 4 discretely displayed values. So now the only way we cannot express that as an interval, okay, because giving that as an interval is going to make people think that it's have all of those values in there. So here we have to write the domain. That's the only choice left. That's the only choice for us. So the domain here is it's a set. There's a 0.5, okay, 0.75, 1.0 or 1.00, and 1.25. So these elements or these members of the sets are being listed in that set right there. And so and that's the only way we can do. That's the only choice for us here to express the domain of our current function, the VM, the function right here, the vending machine function. Okay? And so we found the function. We found the domain of the function. We understand. So that was the basic introduction. So let's now formally, I'm going to bring you into a couple of examples. Okay? And then so the first challenge we're going to face when we're doing these examples, these problems, because when we're studying in pre-calculus or college algebra over here, then any problem itself, I mean any example that I'm bringing through brings up a problem, a challenge that you will be facing anywhere here and there in your study with pre-calculus. And so before I give in this first couple examples here, then I have shown when the function was having a clearly written rule like this, okay, then we knew to express the domain for this was this interval from 0 to positive infinity. And that was when our function is written with a known rule like this, okay. And then when the function was given as a table, similar to the vending machine, we've had values. Okay, so for example, 1, 2, 3, 4, these are the inputs, and then the 0, 3, 1, 5, okay, these are the outputs. Then the domain, the only choice we can express, we express that as a set. Okay, the domain here, these are all the input values. Okay, and so 1, 2, 3, 4. Okay, and we have to express it as a set. So that's how we handle it. And we will get into some later examples as well, but that's how we handle and express the domain. That's why we found the domain and express the domain in set notation. But now, before I really head into a formal example, a lot of times what's fascinating us is how we can find the domain when our function is given as a graph. Okay, so instead of table like what I just erased, a lot of time a function is given as a graph. At this point, anyone should be clear, a graph is a representation of a function. A graph is just a representation of a function. So some function may have a graph like this. Okay, some function may have a graph like this. And so now I have hopefully explained thoroughly enough in my introduction about the graphical representation of any function. Then the convention says the input values are being placed on the horizontal axis. We can call the horizontal axis the x-axis. We can call the the input values the x variable. And so, but the rule that's agreed, the agreement that's agreed worldwide is that we put all of the input variables, all of the input values on the horizontal line right here. Okay, and then from the left to the right, increasingly from the left to the right. And so in this way over here, the domain, graphically speaking, you see, for a function like this, maybe it keeps spreading further, but anytime looking at a graph, the first thing that makes sense to anyone, and I emphasized this earlier as well when I was introducing, that's why I had maybe a lengthy video back then to explain just the basic idea about any function can be represented graphically. But part of what I've emphasized there is that anytime looking at a graph, a very big amount of time, a very high percent of time is that we're going to be looking at the graph from the left to the right. Okay, but the idea now is that any graph has a horizontal spreading, a horizontal spread. Okay, how far it reaches from the left to the right, how far it can reach horizontally. Okay, and so now the domain is the set of possible inputs. So like a domain, like an input here, if we have an input here, do we have a value? If we have a value defined, then it would have a point here. Okay, so this input here was possible. Okay, if we pick a different input, okay, so an input here, do we have is this input on this line right here possible for the function to take, or is this an input that's possible to this function? In order to tell yes or no, we just find out whether it has a value whether it has a point on the graph or here on the curve. And so this input is also possible because it has a point on the graph, and this is the graph that represents our function. So now in that way, allow me to put it all together as a generalization. When you're looking at the graph of a function, the domain, this is my own way of interpreting when you're looking at the graph right here that represents a function, when you're looking at the graph of a function and try to determine the domain of any function, the domain, when your function is given graphically like this, the domain is the horizontal, okay, the horizontal spread, okay, of the graph. Okay, because you see, in the worst case, some function, in the way how it's given, in the way how it's defined and given to us graphically, it starts only from here and stops here. Okay, then will an input out here possible for a function. If we picked x equals a value out here, will it work for the function? See, with that input, this vertical line of mine does not hit the graph anywhere because the graph stops right here. And that's the idea. And so, in other words, the way how I'm seeing horizontally, this graph starts only somewhere about here and stops about here. So this is the horizontal spread of the graph. And that represents the domain of the function. Okay, the domain of this function represented graphically. Okay, and so that's the idea of how we take our fundamental understanding and bring that into, when you're looking at. And we will get into those kind of examples where we will have a function with a specific written rule. Here I'm indicating the function with graph, and I'm more, at this early part of the video, I'm more focused on the kind of function where it's given and represented graphically, and the domain of those functions who are represented through a table right there. Okay, so now we are all ready for stepping into example 1 right there. All right, so let's look at example 1. All right, so find the domain. Okay, find the domain of the function. Okay, with the given graph, or how about represented by the given graph. All right, so that's the wording of this example over here, of this particular example. We want to, so the idea now is that throughout the example, I'm going to be doing about 2 or 3 sub-problems, part A, B, and C. And then each problem, part A, B, and C, I'm going to give just simply a graph that represents a function. We're going to look at the graph and be able to tell the domain of the function. Okay, so now here we go, part A of the problem. So now I'm going to have a graph popped out right here in front of everyone on the screen right here. Okay, so let's now look at this function right here. This function, we don't have to see a specific rule, and that's the intention of this problem, but it has a graph as given here. Okay, and in this graph, in the way how I see it, all right, in the way how I see it, I have explained earlier the domain of any function once is given to us as a graph, as a graphical representation. The domain is going to be the horizontal spread, okay, how far it reaches from the left to the right, how far it can reach. Okay, and so now the graph is given right here. Nobody is required to know whether it's a quadratic function, whether it's an x squared minus 5x plus 10 whatsoever. That's not the important part. Okay, the important part is we look right here at the graph that's given to us. It already represented a function, okay, a function of some kind, and we want to find out what is the domain of this function. And again, our function is only given as a graph right now. Okay, whatever rule, there's a rule. We just don't see that rule explicitly written out for us. That's all there is. Okay, and so now I'm going to bring that into even closer look right here, into full screen mode right here. So the graph of our function in part A is here, and then with decimals, I'm going to go ahead and I'm going to zoom it in a little bit. All right, so scrolling the mouse wheel a little bit up. Okay, and I have a closer look at the graph. Okay, and so in what I said earlier, the domain of a function graphically is the horizontal spread. Okay, the horizontal spread of the graph. Okay, how far, and so this graph is given simply just that piece. Okay, it does not extend infinitely horizontally. Okay, it only stays in a certain, and you're seeing it right in front of you, and you know exactly what I mean right there. Okay, so from the left to the right, it looks like there's a definite start and end of the graph from the left to the right. Okay, so in that way, now I also know this is not formally taught, but I found it has been useful to my students in my past the classes when I was teaching this, and so I highly recommend to use a vertical line. Okay, now vertical line is formally used as a way to detect whether a graph is a function or not. Okay, that's why there was that famous technique that's called a vertical line test. But here I'm using the vertical line again, but for another purpose, and that's why it's probably just me who introduces this technique, but it has not been formally taught throughout many professors out there. So watch out for that. But it's still a very convenient tool for me at least. So here's how I use a vertical line to decide right here. Okay, so now there's a vertical line, you see, and vertical line always, any vertical line always represents the input value, because right now where I put that line, it's at x equals negative 10. And see, you can see that the graph horizontally does not even reach out here. And that's the idea. The graph horizontally stops right about there. And that's why now I'm going to start moving that vertical line a little bit inwards, okay, to the right hand side. All right, and now on my graphing space, you can see that vertical line is moving. But see, anywhere I'm currently moving, it still did not hit to the left start of the graph yet. Okay, and I'm using that term, the left start. And so now we can keep moving the vertical line. And now right about here, when it's x equals 0, we're gonna start interfering with the graph. So now it looks like anywhere between 0 and 5, my vertical line hits with the graph and creates a point on the graph. That tells me that anywhere between 0 and 5. Okay, because for now I'm only looking at between 0 and 5, and I notice clearly through the graph. Okay, and let me bring it in closer zoom right here. So anywhere between 0 and 5, clearly this vertical line right here hits the graph and creates a point on the graph. See, right there I have that point right there, and then I can move that to different places right there. Okay, and that point is still there with me somewhere. Okay, and it's still here. And so, but now outside of that, when I move the vertical line outside beyond 5 right there, see, it no longer hits the graph. And this is where we say, the function is undefined at these values above 5, or the function is also undefined anywhere at those inputs values below 0, because there's no graph that crosses through our vertical line. Okay, and so now but now what about at the two endpoints right here? So anywhere between, now clearly it works, but what about the two endpoints? So now when x equals 0 specifically, this empty hole right here, let me hide that vertical line and zoom it in. The empty hole we've learned through previous course. This empty hole means it's an empty point. X equals 0 is not defined for the function. We have an undefined point right here. So the function does not have a value, does not have a vertical height when x equals 0. Okay, and the function here, the function does not have the same here. The function does not have a height for x equals 5. So x equals 5, it leaves an empty hole right there. And so now in that case, now we are so ready to make that general conclusion. Let me still keep the graph here, but now the domain according to that graph. Okay, now the domain has to be the domain. Okay, is anywhere between 0 and 5. 0 is the left side, 5 is the ending. Okay, start and end, but it does not starting here. Okay, it just stays anywhere between. See, that vertical line has a cross with the graph anywhere between 0 and 5, but does not include 0 because we had an empty point. does not include 5 because it has empty point there, right there that you can still see. And so now I have to use parentheses here. Okay, so this is in interval notation. And again, so that's our final answer, and this is the preferred form. My instruction of this problem did not indicate clearly enough that, and because I was trying to save space here, but so by default we go with interval. A lot of professors in these days are looking for interval notation. So, okay, this is the preferred. Okay, in interval notation. All right, that's by the default, the preferred answer right there in interval notation. Okay, so that's all the reasoning that leads to making this conclusion. We just have to look at the graph, and again, I was using that advice, like the domain of a function graphically is the horizontal spread of the graph. Okay, how far it reaches from the left and to how far it can reach to the right hand side. Okay, and watch out for ending point right there. Okay, all right, so now after that example, let's now erase the board here, erase part A, and let's look at another graph. And so now we have part B. Okay, and so find the domain, and of course at this point in interval notation. So how about I'm going to go back to this problem and make extra clarification, find the domain in interval notation. Okay, in interval notation. Okay, of the function. Okay, represented by the given graph. All right, and so now let's look at part B. Okay, so now all right, so here we go. This is the graph. Okay, this is the graph for part B. So now we're seeing the graph. It could be a line, it could be a waving curve, a waving shape, whatsoever. But now to find the domain, to identify the domain of whatever function given and represented by this graph right here, then we're gonna start looking at the horizontal spread. How far it can spread to the right and how far it can spread to the left. Okay, the total horizontal spread of the graph, left and right, how far it reaches. Okay, and so now let me put it in the closer zoom right here. All right, and so now with a problem like this, all right, and so now I put in that vertical line here. All right, so now I'm going to put in a vertical line, even though you're not required to, but it's highly advised. So here's my vertical line. All right, so think about we are putting, and you can see the line itself is vertical, but I'm moving it back and forth so that I can ensure that anywhere I place my vertical line, it will intersect, it will hit the graph at a point on the graph. Okay, so anywhere I place the line, the vertical line, then the line hits the graph. The line has a point that hits with the graph, and that's why now I can say that, you see, we can keep bringing the line further and further and further and further, and we're still hitting. Okay, and then back to the left. Okay, and back to the left, we can bring the line to the left, further to the left, and it's still hitting with the graph. And no matter how far we go to the left horizontally, and we keep going to the left further and keep going further to the left, it's still hitting with the graph. Okay, now the part out here is outside of our viewing window, but it's still, that vertical line is still hitting with the graph right there. And so now in this case right here, apparently the domain here, it looks like it's all input values in the real numbers. Okay, all input values that's placed on this x-axis, this input axis, this horizontal axis. Any of those input values, when you put a vertical line, it will hit the graph at a point. And so now we can say clearly that the domain for this function, whatever that function is, nobody has to worry about is that a linear function or is that a quadratic function, 2x minus 1 or whatsoever. That's not the important part, but once the graph is given, then we're going to look at the horizontal spread of that graph, how far it can reach to the left and how far it can reach to the right, or maybe it's going to keep reaching out infinitely, like in this case right here, horizontally. Okay, and so now for the graph like this, now I can say the domain of this graph, okay, the domain of this function. And so now, starting with part B, and after the detailed explanation earlier, now I added in that clear indication that we want to find the domain and express the answer in interval notation, okay, of the function that's represented by the given graph. So the domain here is anywhere between negative infinity and infinity. All real values, okay? And infinity, we've learned from the previous algebra course that an interval where any and has the infinity symbol, we're going to use a parentheses, okay? Because infinity itself will never be a finite stop, a finite value, so we cannot include infinity. It's always going to be parentheses, okay? And so now that's our answer in interval notation. All right, and so now we can start picking up the pace here. So now I'm going to erase the work we have just done. And let's look at part C right here. Okay, another graph is going to be given. Okay, and so all right, so now let's look at this graph right here. This is the graph for part C. This is the graph for part C. All right, so we have a function, we have a graph. Okay, but this time, and it looks almost like that line we've had, that graph we've had in the earlier part right there, earlier in part B. But now this graph has only a segment. Okay, so now you went just simply by looking at this graph, looking from the left to the right, anyone will see clearly a sense about having a restricted spread. Okay, it does not extend infinitely on both ends right there. Okay, it only stays in that some certain start from left to the right. Okay, and so now, and to make it real clear again, I highly recommend, and by the way, I'm going to put that in closed zoom again. Okay, so when we're at the complete full screen mode right here, now I'm going to start putting that vertical line. All right, so here's my vertical line. See, anywhere here seems like anywhere before I hit to x equals -2, then there's no intersection with the graph at all. See, so vertical line is here. That's what I want anyone to focus to right now. The vertical line, anywhere I move it back and forth, right, left and right, but to the left of -2, then there's no intersection with the graph at all. And now anywhere between -2 and 6 right here, anywhere between, then the vertical line, our vertical line here will hit the graph at a point. Okay, and so now we know for sure that anywhere between -2 and 6. Okay, so let's put it in. I'm trying to go in slow step again. So for the domain, as far as the domain, anywhere between -2 and 6, -2 and comma 6. Okay, and I'm slowly on my way to finish constructing that interval notation right there. But now let's look even further. Now on the left end, there's an empty hole right there. That means that when we're specifically at x equals -2, there's no defined value. So that means -2 is not included in the domain as well. Okay, that means in other words, it's still the line here right at x equals -2 still did not hit with this red line. That's what it is. Maybe I missed to explain that in earlier problem, but now it's get it clear. The hole just means the vertical line right at that particular value did not hit with the graph here. That's the idea about the hole. So that means as far as the domain, okay, as far as the domain, it has to be parentheses there. Okay, and now I'm going to keep moving. Of course, anywhere between, we're clear that it has a crossing point. But now as I'm going to be, when I'm right at x equals 6, that solid point means we do have a point on the red line right there that meets with the vertical value right there, with the vertical line. So that means now that means we include, as far as values to include, the input values that we input, we include x equals 6. So now that's interval notation. That's the domain anywhere between -2 to 6 like that. Okay, anywhere greater than -2 to 6. All right, and so that's the domain of this particular function right here, given as a graph, given represented as a graph. All right, and so now let's look at another one. Okay, so in part D right here. All right, so here we go. This is our graph for another function, and this is our part D right here. Okay, and so now I'm going to put it in a closer zoom right here, and at this point we can pick up the pace a little bit. So now I'm going to place a vertical line and see anywhere here there's no crossing with the graph. Okay, but now anywhere, if we're going anywhere between -2 and 8 right there, anywhere between that, then the vertical line crosses with the graph. And again, nobody has to worry about what rule is this. It's just some rule. We just don't know the written form of that rule. That's all. Okay. So, but it has a cross between the vertical line and the graph. And now when it's x equals -2, we do have a point due to that solid right there. Okay. And then when we reach to x equals 8, it's still an empty point. So now on my board, this is how I'm writing that answer as far as the domain. Okay. Surely anywhere between -2 and 8. Okay, we take any values between -2 and 8. That's what it is. But then at -2, we do include -2. At -2, when x equals -2, there was a value defined. But when x equals 8, there was no value defined. So anywhere less than 8 is okay. That's why we're leaving that interval there. Okay, so now we have an interval being expressed here. All right, and so now allow me to bring in a couple other quick problems so that we can be able to tell. All right, and now with this graph, we can call that part E of our current example over here. Okay, and again, nobody viewing this video is required to know what rule gives out this graph right here, represented here. All I care is that we have a function already represented graphically, and the graph is given here. Okay, and let's look at the graph to decide, okay, to decide what the domain is. Okay, and so this graph has hidden away some details. Okay, but so let's investigate that a little further. Okay, so this graph does not come with clear solid points here, but it's meant to have a solid point right here when x equals 0. And so now with the vertical line right here, with that vertical line, see, we can see that it starts, see, anywhere less than 0, there was there's no crossing, there's no intersection between the vertical line and the graph. But anywhere, see, when x equals 0, the graph does reach and hits with that vertical line. And then anywhere greater than 0, okay, and anywhere greater than 0. And then this graph has no stop on the right end. Okay, I can just keep moving it out, zooming it out, and then moving it to the right hand side, and the graph is still we can still bring the vertical line further and further. Okay, and so now, in other words, for this graph right here, for this function right here, okay, for this function, the domain of this function is anywhere greater than 0. That means we're writing that as between 0 and positive infinity. Okay, but then as far as 0 value, we do accept 0, we do include 0, and we put parentheses here. Okay, and that's another one that, you know, brings up that for us how we get that interval from a graph, that interval of domain, that domain interval from a graph. All right, and so now outside of this particular example, now we're done with example 1. But with that skill that we have learned in example 1, I've talked about the toolkit functions when I was introducing that basic idea about any function has a graph. And so now I'm not going to go through the entire list of toolkit functions that I introduced in that earlier video lessons there, but let's look at some toolkit functions. Okay, back to the toolkit function. And so if anyone not sure what a toolkit function is, it's just a term I use with my students, a term I use in my video lessons here to indicate these are the very common functions that you must have seen quite a few times prior to entering this course, and we will be using a lot of problems based on these functions right here, very commonly found like that. Okay, so now let's look at this function, f of x equals x. Okay, so for a problem like this, I call that it's a simple, it's the identity function. Okay, the identity function. And so all right, so this is the graph for our identity function here. That's the graph for f of x equals x. This is toolkit function right there that you're seeing. Okay, so now for this particular toolkit function here, then we are now clear that, and as I said, after I'm introducing a few, okay, now I want my students or viewers, whoever want to study this formally, you're going to go through the whole list of toolkit functions out there and identify on your own based on the advice I've been given and the demonstration I've been given through the example 1. But we're going to identify the domain through the graphs and for these some of these toolkit functions. Okay, and so in the way how the graph looks, the domain of this function is anywhere between negative infinity and positive infinity, because, okay, so now with the graph I'm going to put in the vertical line. Okay, all right, so let's put in a vertical line, and now we can see and predict that no matter how far left and right, no matter how far we trace our vertical line out, no matter how far to the right we put our vertical line, it's still going to hit the graph at some point. Okay, and this is the graph specifically for this function, the identity function. Okay, and then to the left, no matter how far we bring that vertical line to the left, it's still going to hit the graph at some point. Okay, and so let me briefly bring that into a full screen view right here so that we can have a better picture of that. All right, so in this way, see, moving my vertical line left to right, back and forth like that, I can see that it's anywhere I'm moving the lines, anywhere I'm placing that line to, it has a point that it crosses with the graph, okay, on the graph itself. And that is how I came to this conclusion that, so for this identity function, the domain is all values of x, all input values in a real number, okay, in the real numbers. So that's the domain for this toolkit function. Okay, I'm going to go over a couple other toolkit functions, and then for the rest of the other toolkit functions that I have introduced in the earlier the video lessons, I want my viewers, I want my students to investigate, to explore the domain and to find out, to discover the domain on those functions on your own. Okay, and so now after this identity function, let's look at this square root of x function. Okay, with this square root of x function. All right, so square root of x function right here has the following graph, and now you're going to be surprised about this. All right, so here we go. This is, ladies and gentlemen, the graph for that simple square root. Okay, square root of x. And indeed, as a matter of fact, this was already brought in as part of our example 1 earlier. So this graph right here is the graph for our square root of x. When we were in example 1, I did not need anyone to worry about what rule that was, because we're simply looking at the graph. We learned that skill to look at the graph and be able to tell the domain here. And so now I'm telling you that truth is this function, this square root function, simple square root function, has that graph as given there. Has that graph as given. So now let's find out what that domain is. And so we can, at this point, we can just use that result we have pulled out from example 1 that we just finished earlier. So the domain here, according to what we found. And you can still look at the graph right now. So the domain is anywhere from 0 to positive infinity. We will never put brackets on infinity, so parentheses is a must. Okay, but we do accept 0. We do include 0 because x equals 0 is defined here. And we have also brought this up. Okay, and this is now this once again to reinforce our understanding when I brought this function up earlier. Okay, even before we got, when I was only introducing about what a domain is. Okay, so this is the domain for that function. When we have seen that and we investigated that graphically. Okay, and so now let's look at the following function. How about f of x be 1 over x? Okay, this is another toolkit function out there, and this is our third one that I'm going through right there. So with this reciprocal function, this is called a reciprocal function. Here's the graph. Okay, so we use a lot of time, we use for these toolkits function, we already knew the graph. So let's quickly use the graph, okay, to identify the domain of these functions right here. All right, so now I'm gonna bring the empty graphing space on screen right here, and all right, so here we go. This is the graph. All right, so this is, with this particular problem, this is where, you know, when I introduced that technique about using the vertical line, somebody agrees, somebody doesn't. That's completely okay. But in this example, it's a good place where you're gonna get really convinced that the vertical line is a good tool for using it. Okay, you don't have to blindly believe any instructor. I mean, whatever they're being taught. Still, in the end, you've learned the lesson. I mean, you've learned it, and you can explore that and blend it with your own style of approaching it. Okay, not every instructor will give an advisor that works for everybody, but at least, you know, at some point we're experienced enough that we can point out a couple of tools, a couple of resources, a couple of advice that make it click better for any one of you learning. Okay, so now here's it. I can see that my vertical line tool is particularly useful here. Okay, all right, so now anywhere to the left of this x equals 0, my line has a crossing point with the graph. Okay, and look at that behavior right here. Now let me really zoom it in at that behavior nearby 0 but on the left, as I'm moving my vertical line closer, and now it's a good time to put it on full view right here, full screen view. But as I'm coming closer, okay, now as I'm coming closer, okay, the vertical line is still hitting, and as I'm coming closer to 0, okay, as I'm coming closer to 0, it's still, all right. The value keep flowing down. The crossing point is still there, but being really far down. Okay. All right, and you can see that we can have at pretty close right here, we can still have a value that crosses with the vertical line way down here somewhere. But then in the end, when we exactly at 0, okay, there's just no value. There's no place on the graph that crosses with this vertical line. Okay, right, only at x equals 0. only at x equals 0. I pointed this out in a very early problem that, when we had this function f of 0 was undefined. And here is what we're seeing it graphically. Now, outside of x equals 0, anywhere else works. Okay, so now let me bring that into, see, now on the right hand side of 0, when an input is greater than 0, it's still going to cross. Okay, and it can come real close to that. See, now I'm at a really close place with the graph right here, and it still cross. Okay, and I can even be closer. But the graphing device I'm using here will also fail to display all that crossing because it cannot tell the difference between the red line and the vertical line anymore. Okay, but in the end, my point now is that, see, this is what you're seeing, that only right at x equals 0, we don't have a value, but anywhere else there's a crossing point. That's why we won't even be able to put an empty point. Okay, we can't even put an empty point right here. We just have to leave that there. The graph just won't cross through. All right, so in that way, now as far as the domain. Okay, now sometimes the logic says we want any x value other than 0. That's one way of expressing it. I mean, that's one way of communicating it, one way of reasoning it. But as a final answer, by default in interval notation, this is how I'm seeing one zone, one region, okay, is to the left side, one interval is to the left hand side of 0. All right, and so anywhere from minus infinity to 0. That's one portion, one zone right there. But we also have another zone. So one domain, but it's got two separate zones right there. There's another one that's from 0 to positive infinity. Okay, and let me quickly pinpoint that out right here. All right, so in this area to the right hand side of x equals 0. And so now, and we won't include 0, that's why it's parentheses here indicated. And so now, and you have learned from your previous course that when there are two disconnected intervals, but we still need to take them both, we use a union sign right here. So this says either we're in that interval or in this interval. If your input is in this interval, or this is or in that interval, either one of these, okay, then it's possible any inputs in either one of those two intervals, it's possible to be given into the function as an input value, to have a defined value outputs coming out. Okay. All right, and so now let's have a look at one more toolkit function with the graph, and so that we can identify the domain right here. All right, so the function I'm about to introduce here, the toolkit function I'm about to get to, is the x squared function. This is the basic quadratic function. The simple quadratic function right here. Okay, so here's the graph of that. All right, and so now that's the graph for this simple quadratic. All right, so now again, to identify the horizontal spread right through the graph right here, I'm going to use a vertical line. Okay, and right now where I place this vertical line, now the viewing window is not telling the true story, but it will cross, because you can see that the graph itself is kind of heading out, right, slanted out right there. So if I zoom it out further enough and keep adjusting my window right here, okay, then you will see that you can see that the red line and the vertical line comes closer and closer, and yes, at some point the two crossed each other. Okay, and then I can bring it even further. Okay, then yes, it will have a crossing point again. Okay, another crossing point like that. And so, in the same way with if I bring this vertical line to the left hand side, okay, so these are easy to see due to the viewing window, but as we go too far out to the left hand side, it's becoming harder and harder because it's kind of hidden above the outside of the viewing windows, but it will cross. Okay, so in this case, now we have our evidence that to say that the domain of this function, okay, must be anywhere from minus infinity, anywhere between minus infinity and positive infinity. Okay, so, or in other words, anyone can say, I mean, the domain for this simple quadratic function is all real values, okay, all input values in the real numbers. Okay, and so that is how we can find the domain, okay, of a function through identify the domain of a function and express that in interval notation through a graph. And we have investigated the domain of a few toolkit functions. So what about the other toolkit functions that I introduced in my earlier lessons? After viewing from this, you can independently, anyone who is studying with me can independently explore or discover the domain from those other toolkit functions that are not covered here. Okay, and you use that vertical line, or if you don't like that vertical line and you already have a quick way to judge the horizontal spread of your graphic there, go with that. Okay, but the point is just stay with that advice I've had. The domain graphically is the horizontal spread of your graph. Okay. All right, and so now let's turn our attention over to looking at what the range of a function is. And we have still not thoroughly covered all details regarding the domain yet, but now it's a good time to start blending in our understanding of the range of a function. And then at a point later, after doing a few examples or a few example problems specifically about the range, then we're gonna start looking into those problems where we just find domain and range together. Okay, and so now, so to start understanding about the range here, now first let's roll back to again some of those the functions that I have introduced in the early lectures where I start introducing about what a function was. Okay, and so let's look at a function like the following. So let me bring out this example in this case right here. Let's say, how about we're looking at a function x squared, okay? And if you may know this or you may not, that's okay, but this is also one among the toolkit functions, okay? But and you can call it, I mean, you know the name or you may not know the name, that's still okay, but this is called the simple quadratic function. But so once the function is defined, okay, and admittedly, this function here, admittedly, you should be able to tell that the domain of this function is anywhere from minus infinity to infinity. So the domain takes all real value. Okay, so that's about the domain. So let me quickly give a demonstration. So right here in my empty graphing space, this is the graph for that toolkit function that I brought up right there, which is also an introduction to the idea of what the range of that function is. Okay, so now that's just quickly as a brief look at the graph of that current function. But now let's return to this problem here. So domain was the set, according to the definition I wrote down earlier, domain is a set of possible inputs to a function. So the domain of this function is the set of possible input values to that function. Okay, and we already at least up to that basic understanding we're through. Okay, but now let's say once you know that you're in the domain, once you know that you pick values in that domain, now it's time to look at the outputs. What kind of output values are coming out within the domain here? Okay, so just earlier as something to raise our awareness about, now I had to erase to write it in a different space right here, but our domain is any value on the line of real numbers right here, all values from negative infinity to infinity. So now that let's look at a value here. Let's say I'm going to pick an input, -1. So this is an input. So this value surely came out from the domain. But now let's investigate the output. So with this function right here, the output is f of -1 according to the rule of this specific function. Then it's going to be a -1 all square. Okay, because the rule of the function says we square this particular inputs. So now at this point, the whole idea about being aware of the domain is that any inputs, you got to be aware that any inputs that you are able to evaluate or substitute into the function must be the input that came out from this given domain or from this known domain. Okay, but now we're putting a pause on our domain discussion right here. But now let's say, now as you know our domain, we're gonna pick a value, an input from that domain, and we're looking for the outputs. We're investigating the outputs. What kind of behavior is the output gonna be? All right. So in the way how this rule says, we have an output here, it's a positive one. Okay. So negative gives a positive output. Negative input gave a positive output. Now, let's try a different one. How about a 0? This is an input. F at 0, that's how it says, that's how we say the notation. The rule says for this given input 0. That's just the notation, but now into the actual rule, we square the input, and we come out with an output being a 0. Okay, and now, so I try a negative input, and the idea is also try to start thinking outside of the box. Here I'm using -1. But outside of -1, think about generally this -1 represent any negative value. So the square operation, and the square specifically on the entire input, made the output being the output be a positive value. Okay, and then for this specific 0 input, which also came legally out from this domain, this known domain, this found domain, then this input, at this input 0, the function, according to its rule over here, gave an output being 0. And now in that way, since you're seeing where I'm going, then let's look at another one. 2, how's that? Okay, I could have chosen 1, okay, but now I decided to use 2. Okay, so a positive value, the rule of the function says we're squaring this input, and even though there's no negative, we're squaring that input, and even though there's no negative sign, which makes no difference, but I'm still using the parentheses to indicate that. So I substitute this specific input into our input variable x like that. So the output came out being a positive value. So we tried a negative value. Here it was -1 specifically, but it represents any negative input. Any negative input being substituted into the function gave a positive output. And this positive input right here, I could have done f of 1 as well. Okay, it was again another positive input from the domain, from the known domain here. And then the rule of the function says we're going to square that input, okay, and equals 1. And again, that output is a positive value. Positive output, positive output. Even any negative value as an input would give a positive output. It's just the way how this function is. It's just the way how that function is. And then 0 specifically give an output being 0. So it's so far within a few tries. These are just some trials. Within a few tries, it looks like the outputs, and then generally and traditionally enough, and so I highly recommend to be more flexible than just sticking with x and y. But you know, with this specific discussion, and there's nothing bad about sticking with the tradition. So traditionally we use the y to represent the outputs. Okay, so y equals and y equals. So y as an output here equals 1. Y as an output for this case right here, where inputs was 0, equals 0. This is y equals 4. This is y equals 1. So far throughout all the trials I have seen so far, y is either greater than 0, being a positive value, positive, 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 or so far the least came down to 0. Okay, or so far the least come down to 0. And we can try y equals the function at input -5, for example. Negative input, again, I purposely try to put in a negative input. Okay, let's see what's happening. -5, but being all square according to being all square or being squared entirely, including the sign. Okay, and according to the rule of the function, we ended up with positive 25 again. So that's once again came in consistent, right? Appears to be consistent with our observation right here again. So far it's not a final conclusion yet, but at least I see this as, you know, I've had this as an observation. Okay, through the observations, observing these output values so far, we either get a positive value or 0. It's the lowest so far for all these range right there. So range, I mean for all these outputs right there. So I'm a little rushed to talk about range earlier, but we will formalize the idea shortly after this. But now, right now we are aiming at the outputs values, the behavior of all these output values right there. Okay, and so after a few tries, we're going to start questioning ourselves. So is there any possibility? Is there any possibility that we're ending up with for this function? Okay, so we came to the observation, and I wouldn't rushly say that this is the conclusion yet. Okay, but at least now after a few tries with positive input, with negative inputs, and even with 0. Okay. Can we, for this function, okay, can we have a negative output, okay, or a negative y value? Because as agreed earlier, let's stick with the tradition here that we use y as the output value for this, for any of these problems here. Then does it look like we can? Does it look like we can? Because see, throughout we've done only a few tries, but at least those tries have been representative enough. Okay, it's been illustrating the idea that see -1 for the input and -5 for the inputs generalized the idea that plugging in any negative numbers, which is everything in this domain. What's in this domain? Negative number, positive number, and 0 in the middle. Okay, and we try any random. See, I picked 5, I picked -5, I picked -1 as on random basis right there, and they all gave us, gave me positive output. And I switched over to try the positive value. They're all in this domain, and again the output came out being positive. And I tried 0, and the output came out 0. And so in this way, the answer to this, predictedly or projectedly, no, we can't find really any negative output. No negative output at all. Okay, and so now let's quickly have a glance at the graph right here. Okay, and then we will come back and talk more about the graph, how to identify the range from a graph. But here, and I didn't even talk about what a range is yet. But now, at least for the outputs, recall from my earlier video lecture that I pointed out that for generations of math people, for generations of mathematicians, and we are doing math, we're all math people. Okay, generations of math people agreed worldwide that we put the vertical outputs, we put the output values on a vertical scale. Okay, and that's the reason why right here in the picture you're seeing the vertical axis right here, and in our case we call that we name that the y value. So the vertical axis you're seeing on the graph here is the axis that has all the output values. Okay. And so in that way, let's observe that a little more closely here. And you can see that, you see, vertically, this graph vertically, and this is, by the way, this is the graph for our famous simple quadratic function. And since we have already agreed that to find the outputs, to understand the outputs, when we're reading a graph like this, right, it's represented by the vertical, on the vertical scale, on the vertical axis. And so in that way right here, vertically speaking, this graph does not go anywhere below the x-axis here. And right where it hits the x-axis, right when it hits the x-axis vertically, that is, this is y equals 0 here. Y equals 0 is the x-axis. And now you can see that there's no other part that sinks below the x-axis. That means this graph here, the way how it is making it consistent with the fact that with our observation we've made previously. All right, and so now again, there's a zone. See, now we're talking just strictly on behalf of the output value. So for the output value, in the way how our function was defined, there's also, it naturally lead, or it consequently lead into a restriction of output values that we can possibly get. Okay, it just naturally lead into that. So some function can generate all kinds of output values from negative infinity to infinity within the domain. But some other function, like this case right here, only produce, okay, this function only produces output values anywhere from 0 to from anywhere from 0 and up. Okay, anywhere from 0 and up. All right, and so now in this way right here, so after making that observation, okay, all right, so from making that observation, now I'm looking at, so here's let's make some note here. So after we were looking at that observation, now I can make some conclusions for this function, the only possible. See, now I underline that term again, the only possible output values are anywhere, okay, 0, including 0 and up. Okay, that's just like what I was saying earlier, or mathematically speaking, y greater than or equal to 0. That's what we saw right there. The only possible output value, but we're only considering the possible output values. It's the way it is, the way the function is, create that situation right there, consequently. Okay, and so now in that way, now we come to the formal definition of what it means by being the range. Because now it's all of these possible output values. Notice the plural right here. So all the possible output values together make up a set, a zone again. So earlier when I was talking about the domain, then the domain was also a zone of values. The range, what we're about to get into, is also another zone of values. And graphically speaking, when we were looking at domain earlier, the domain is a horizontal display, a horizontal zone, horizontal spread of where your graph is. Okay, and so now we're heading into, it's another zone, another kind of zones, but the zone of possible output values, the zone where on the graph it displays all the possible outputs. And the possible output values, I keep making that, I've kept making that physical demonstration right there. It's the vertical values, the zone of vertical values right there. Okay, and so now in that way, now I underline that term possible, because there's some outputs is entirely impossible for the, say for example, this function won't make any negative outputs. Okay, so that's impossible. So there's a zone of possible outputs and there's a zone of impossible outputs right there. Any function has that situation depending on the way how the function was defined. All right, so now for everybody who's learning from this lesson right here. So now we come to a formal definition of what the range is. Okay. So the zone of possible outputs, we refer to those to that zone right there as the range of the function. Okay, and so just like how I explained earlier, I found this the way of wording from this one particular textbook that I'm using right here, which is quite consistent with my own way of explaining things right here, explaining about domain and range. So allow me to use the wording from this specific textbook that I'm using here. But so the range here is represented as, the range is itself the set. Okay, that zone I've been talking about is a set of values. In formal terms, okay, in formal math terms. So the range is the set of possible. Okay, see, I made that demonstration earlier about possible or impossible to be in among the outputs that can possibly came out. So the set of possible output values, okay, of a function. That's what the range is. Okay, it took me a lot to explain because I want viewers who, once you finish viewing this video, I hope, and my main aim is for you to get the core understanding and the fundamental understanding, step-by-step understanding of these building block understandings right there. Okay, domain and range. Okay, for learning, you definitely don't want to rush any of your learning right there. So take your step and investigate and explore the way how I explain these. All right, so the range now, formally speaking, the set of all possible output values of a function. That's called the range. It's one nice short term. Okay, and so now that means back to that quick little function, f of x equals x squared right there. Okay, now we already knew that the domain in interval notation, negative infinity to infinity. Okay, and just now we got through the definition. And so just like that, as a reasoning, as a logical reasoning, then for this function, the outputs as a y value came out only anywhere 0 or above. This is what it says here, y greater than or equal to 0. That's the logical reasoning, the mathematical reasoning. Okay, and y greater than or equal to 0. Now on the vertical scale, even though I draw the horizontal axis as well, but 0 is right here. Okay, so when it comes to this, maybe I'm the only one doing this kind of thing right here, but 0 or above. But here we're talking about a y value, and outputs is the vertical is placed. Any output is placed on the vertical scale right here. So that means anywhere from 0 is here, right on the x-axis, or right at the origin, but and up. Okay, 0 and up. And we do include 0, so there's a bracket right here. All right, so I'm using a brackets too, but I'm using a brackets that covering from the bottom 0 to up only. We won't find anything below that. All right, so now in interval notation, so this is just a way for you to explain things to yourself, a way to make reasoning. But it's not a way to present as final answer. Very similar to how we have done that back in the earlier part of this video lecture where we were doing finding domains. So now we're finding range. But this way is not the way to express your final answer. This way is also not the way widely accepted as a final answer. So the way to express your final answer as for the range of this function, we say it's anywhere from 0 and up. The wording is saying that, so 0 to positive infinity. Okay, but 0 is included because we did have, according to the demonstration I made, we did have an output being 0 specifically. Okay, and then anywhere else it's just positive values and positive values. So now including 0 and anywhere above, that's the range. Now it's in interval notation. Okay, so this is the preferred form. Right? So the idea, the logical idea now is that within these inputs, or for any inputs within the known domain here, this function only came out with values. Only came out with possible values anywhere from 0 to infinity, to positive infinity. Okay, and so this is interval notation again, and this is the preferred way of this is preferred by many professors, including me right here, when it comes to grading my students' paper. Okay, this is the preferred answer format, and again, this is interval notation. All right, this is interval notation. Okay, and so now with that function here still being given here, I gave, now let me clear out all of that, these extra details here. And so now when it comes to investigating because a lot of times it will come to that kind of problems, okay, that kind of challenge where a function is given to you, okay, and we need to identify from the graph, from the given graph of the function to find the range. Okay, so in that reason, let's swing back. I'm still leaving this function here. Let's swing back to the graph of that function. Okay, and then to understand a little more about how we can understand the range of a function through the graph that's previously given. Okay, so this function has the graph as seen here. That's the graph for the function. Okay, so with that graph that you're seeing, you can see that, and again, it is agreed internationally that outputs, which is what we're right now focusing to, outputs are placed on the vertical scale. So in this way, the range defined as the set of possible outputs. And I just now noticed that I had a little typo here, but I meant to have, this is outputs, okay, output values, not just output values. So the range is a set of possible output values of a function. But now outputs, just now again back to what I was in the middle of saying, outputs are placed on the vertical scale. And the range is like a whole zone, the set of possible output values. So now on strictly looking at the range on a graph from the graph of a given function. Then now let's have a look at that right here. So the graph, with this graph right here, the range is seen as the vertical spread. Okay, the vertical spread, how far the graph can spread up and down, how far the graph can extend up and down vertically, up and down. See, domain, we go left and right because it's horizontal spread, as I interpreted earlier when it came to when it was domain, when we were still talking about domain. But now it's the range, so it's vertical spread, or how far up and down our graph extends. Okay, our graph can reach. All right, so in that way, and with the graph being seen here, okay, let me swing back to the board and make that note right there. So the range here, I'm going to say, I would just like that. I should have done in red ink for the domain earlier. But graphically, okay, the range, okay, is the vertical spread, okay, vertical spread of the graph. And of course, we must understand that it's the graph of the given function. All right, and so now we are ready to be facing our next challenge here, or one of the first problem that we identified the range from a function that's given as a graph. Okay, so allow me to erase the board and spend some time writing down the wording of the example. All right, so here we are at example 2 here. All right, so now according to the wording, let's say we want to find the range. Okay, find the range. I underline that term right there. Find the range of I would say find a range, and of course in interval notation. Okay. Of the function. Okay. Represented by the given graph. All right, and so now the plan for this example is just like what I did in example 1 right there. We're going to look through a few different graphs, and each one of those graphs is the representation, the graphical representation of a function. And then, those are part A, B, and C. Okay, and then from each of those graphs given this time, we're going to be looking at the range, the vertical spread Okay, and then along the way, I will be I'll be introducing some good tricks and tips and tricks somewhere here and there, so that it helps identifying the range easily. Okay, but keep in mind the range vertically, the range graphically is the vertical spread of the graph. Okay, so now let's look at the graph for our first function in part A right here. All right, so here we go. This is our function for part A. This is the graph of the function in part A right here. We don't have to know what rule is this function. There has to be a rule that creates this graph, but it's not important to know that. So now let's say the function is already defined and it's given to us here as a graphical representation, and that's what we see here as a graph. Okay, so now let's find the range. Let's find the range and express the range once we decided to express that range in interval notation. Okay, and so now looking at the graph, so my advice earlier is we're going to be looking at the vertical spread of our graph right here. All right, so now in a full screen view right here. Okay, this is our graph, and I'm gonna scroll the mouse wheel a little bit to zoom it in even further at a closer zoom right here. Okay, so now when it comes to this, okay, somebody can quickly see that the vertical spreading of the graph seems like the lowest part of the graph is down here at 2, the lowest, and the highest the graph can reach, because nothing else vertically above this point. So it looks like anywhere for now between 2 and 11. Vertically, between 2 and 11, we have the graph going through vertically. Okay, but really to make it clear, crystal clear, solid clear, then I introduced it. This is just probably me introducing this, but I introduced the horizontal line technique right here. This is not a widely taught technique, but allow me to introduce it. It has been at least very efficient for my work and when I teach my students specifically. But now, let's say when you are looking at, let's place a horizontal line. Okay, so I'm going to use a horizontal line. Now it's a little bit counterintuitive here, but we're measuring. See, just like domain, we were measuring horizontal spread, but we were using vertical line. So here we are trying to measure. We're trying to investigate. We're trying to detect where the vertical spread of the graph stays. Okay, how far the vertical spread of the graph is. Then in that way, we're going to use a horizontal line. We use horizontal line and bring it up and down to detect. Okay, so now let me graphically show the picture. Okay, so here's my horizontal line. Okay, so see, think about it. When this horizontal line is being placed at somewhere low enough, then it's not even crossing any point of the graph at all. Okay, and this is where it's telling me a good sense that at where I place my horizontal line right now, it's outside of the range. The range didn't hit the range of this graph. This did not hit down this far right here. Okay, and now once we're all on this, once everybody is agreeing with me now I can start dragging my horizontal line a little bit up. Okay, so now clearly speaking, if we stay inside, when we stay inside, see, that's where I'm moving this, the horizontal line up and down here. If we stay inside in about anywhere between 2 and 11, if we stay anywhere between that, then our horizontal line does cross through the graph at a point, at least at one point. Okay, don't worry about it's crossing at 2 points, because a horizontal line can cross a function at multiple points. That's actually okay. Okay. But now in order to detect the range right here, then just simply bring that vertical line up and down right here. And as long as our line is still crossing with the graph, then we're still inside the range. As long as our dotted, the horizontal line here is still crossing the graph at some point, right? See, right here it's still crossing. Then this value 3 is inside the range. Okay, bringing it a little bit up. Okay, it's crossing and bringing it down lower, like down here. It's still crossing like that. So it's this value about 2 point something, between 2 and 3. It's still inside the range of our function. And so now, clearly speaking, this is why back in the this is for this function right here. Now I'm gonna start saying the following. I see for clear with and now with that horizontal line making the story real clear. As long as the line is crossing the graph at some point, and that place where we place the line is in the range. Okay, that's how we detect using the horizontal line. So now I'm going to start saying the range. I'm going to start making my conclusion. At least what caught my attention here is anywhere from 2 to 11. Anywhere, or how about this? Anywhere between 2 and 11. Anywhere between 2 and 11. Okay, and now in that way, and keep in mind again, we're detecting vertical values. Okay, that's possible that's possibly coming out from this function. And so with my horizontal line being dragged up and down right here. Now let's look at the very bottom right here. When it's 2, when it's y equal 2, is y equal to part of the range? Is y equal to in this set of possible output values? Okay, so now notice, let me temporarily hide that line away, but there's an empty point right here. That means when y equals 2, y equal 2 is not an output value among the possible outputs. That's what the empty point here is for. You know, when it's come down to y equals 2, we don't really have a value defined there. Or in other words, there's no value, there's no inputs that define y equals 2 here. There's no inputs that gives y equals 2. That's why there was that empty point. Okay, and so in that way, now back to my interval here. Now clearly things are between, right? Values, output values are between 2 and 1. But now do we include 2? Nope, we don't, because there was an empty point right there. Okay, but I'm talking about the vertical behavior of that. Okay, now do we include this right end right here? This upper end, this is lower end, we did not include. Now we're done with that. So what about the upper end right here? Are we going to include that? So now once again, now I'm going to switch to full view of the graph. Let's drag the horizontal line all the way up. Okay, keep dragging to hit 11. Okay, so does the line here, does the line cross the graph at y equals 11? It seems like yes, the graph in red and the horizontal line in black right here do meet at that value, at that x equals 2 right here. Okay, when the input equals 2, it has this point, it reached to that point y equals 11. So now in other words, okay, so in other words, we do include the y equals 11 in our range. So this is our final conclusion. The range for the functions given in this graph, represented in this graph right here, represented by that given graph, is anywhere above 2, anywhere above 2 and up to 11, okay, or anywhere between 2 and 11, including 11. That's another way of saying it. But that's why interval notation is quite convenient. Sometimes it's just one symbol, people will understand. Okay, other than, rather than when you're saying, then there are quite a couple ways of saying, and some way of saying it may make, may make people more confused. Okay, but that's the answer to this first graph right here. The range is from 2 to 11, including 11. All right. And so now I am going to erase the board, and let's make space for part B right here. All right. So part B. All right, so here we go. This is the graph for some function, the graph that represents some function. And we use this graph here as our example problem B right here. Okay, so whatever function that is, yes, there was a rule, there is a rule, but knowing it or not, that's not important. Okay, what matters for us here is that, let's say once the graph is already given to us, right? What's the range of this function? find the range of this function here. So again, the range, anytime we're looking at the graph, anytime we're trying to identify the range from a graph, from a given graph, look for a vertical spread of your graph. How far up and down your graph can reach. How far up your graph can reach, as well as how far down low vertically your graph can reach. That's why it's up and down, the vertical representation of that graph. Okay, so in that way, with this graph right here, now let's bring it into full screen view right here. All right, so here's our graph in full screen view right here. I zoomed it in a little more. The x-axis is here, the vertical y-axis is here. Let's now use the horizontal line. See, so the horizontal line to me has been a very effective tool right there to detect the range. So here I'm going to use that horizontal line, and right now from at where I place my horizontal line, it already crossed that graph in red ink right there. Okay, so this is where I place my line at right now, y equals 1. Okay, and now I'm going to start dragging it up and down, and it looks like so far, and that's why, and in these days, having powerful technology is such a gift for any one of us. I mean, thanks to whoever that engineer who created, or that team of designers who created Desmos here for me to use in these days in my teaching career. But see, now as we drag the line up and down, the horizontal line up and down, anywhere we're dragging our line through, it's still crossing the graph at some point. And now, believe it or not, let me really zoom it out far, okay? And then, you see, so that we can have more view. And so let's bring it even further up, a little bit more extreme right here, and it's still crossing, see? Okay, and I brought it up pretty high and almost jump out of the viewing window here, and it's still crossing. Okay, and now let me bring it down even really far low right here. How about, see, really far low right there. Now the line goes really low. No matter how far down low it is, it's still crossing the graph at some point. Okay, the horizontal line is still where we're placing it and where we have been moving it. Anywhere we moved it, it's been crossing the graph in red. Okay, so in that way, now I am clear. Okay, now I am certain that this graph here, from this graph, the function has the range being, okay. And now, before I can write this down, you probably have that in mind already. Anywhere from negative infinity to infinity. It seems like there's no limits on the top and there's no limits at the bottom. So this has to be what it is, vertically, this interval. And then, of course, when it's infinity, then we have to use a parentheses. And that's our range for this particular function right there. Okay, and so now let's look at, and so at this point, part B went on a lot faster because, you know, once you've done part A and had a clear understanding enough, then for the rest of the example 2 right here, I can keep getting faster and faster in the pace. Okay, so now let's look for the range in another graph of another function given by a graph. So how about part C right here? All right. So now let's look at this graph. Okay. So this graph, again, we don't have to see the actual written down rule for this graph that's represented by this graph. But at least what I can see, it's a graph. Okay? It's a graph. You may recognize or you may not recognize that exact same line that happened in part B, but now it's only a restricted line. That means it does not extend forever. It does not extend infinitely up and down right here. There's a certain stop vertically and there's a certain stop at the bottom vertically as well. Okay, so now let's have a look at that. All right, so now allow me to bring you into the full view, full screen view mode again. All right, so again, I'm going to use my horizontal line. Quite an effective tool right here. All right, so I'm going to bring in my horizontal line. See, right now my line is currently outside. I mean, right now where my line is at, my horizontal line in dotted black ink right now, then it's not crossing with this graph at all. So that means anywhere below, looks like anywhere below -2 is not in the range. Okay, so the range, it looks like in this way, the range is anywhere between -2 and 2. Between -2 and 2. Okay, because see, anywhere between -2 and 2 vertically, you can, with this motion of my horizontal line up and down right here, then anywhere between -2 and 2, that's, we have the, the black line, the black dotted line crosses with the, crossing with the graph in red, like that. Okay, so in that way, now we can start making some sketch of the idea right here. The range for this graph, for this particular function given as a graph right here, then the range here has to be anywhere between -2 and 2. Quite clear. Okay, and now let's see if we can, which end here can be included or neither. Okay, and so in that way, now again, in the way how I see it, that when when y equals -2 down here, when y equals -2, there's an empty point. So when x equals -2, it was not defined. Okay, so we don't have an input that defines this y equals -2 value. Okay, and so this empty point now is indicating that the bottom end has to be open parentheses. Okay, we're going anywhere between -2 and 2, and we're not including, we can't include a -2 for the lower end. But what about the upper end? Okay, the upper end, now on the graph here, the upper end does hit into a solid point right here. That means we do have an input. We do have an inputs that satisfy y equals 2. Whereas earlier we could not find the inputs. Is that -2 that gives output to -2 here? We don't know. We don't have an input that satisfied y equals -2 down here. And that's why it was empty point. But now I'm talking about this solid point. In opposite from this solid point right here means we do have an input, and that input is right here. It's x equals 6. Input equals 6. It gives output equals 2. That's why we had that the point, that solid point. So in this case, it means the outputs equal 2. The outputs being 2 is included. And so now that's how we complete our interval. Okay, and so this interval over here is the interval notation for the range of our problem, and that's how we're finished with this problem. Okay, and that's part C of our current example. Okay. All right, and so now I'm going to show a couple more problems in this current example right here. All right, so now here comes part D of our example. So part D is another graph of a function given as the one given here. Okay, and so now we want to find the range of this. All right, so now the range, once again, vertical spread. How low vertically does our graph reach down, and how high vertically does our graph reach up. Okay, and so in that way, let's switch over to full view mode right here. And again, I'm going to use a horizontal line. See, so somewhere down here where I place my horizontal line initially, then it's not interfering, it's not crossing the graph at all. So anywhere down here below 0 doesn't count. I'm going to move my horizontal line a little bit up, even up to +1, y equals +1. It still did not cross the graph in red right here. So now I'm going to see that it has to be, see, 2, y equals 2 is right here. And we start hitting with the graph. Okay, and then now when I keep moving it up, it's now going to start getting into crossing the graph here. Okay, and then it looks like no more crossing the graph beyond when it's above y equals 5. Okay, and so that means with this horizontal line is telling the story, we can see that the range here estimated from the graph. Okay, the range has to be anywhere between 2 and 5. Anywhere between 2 and 5 for now. Okay, anywhere between 2 and 5, that's for sure. Okay, and then let's look to see if we can include the bottom and the top right here. So as far as the bottom, what about when y equals 2? We do have a solid point. Now it's a little confusing that there's an empty point here, but that's not the only one. We have another y value equals 2 right here, where input was -2. So when input is -2, it gives me a y value being 2. Whereas here, it's not necessarily input h to give y equals 2, but at least we have one output. We still have an output at y equals 2. That's why now back to the conclusion here. Now on the left end, we do include y equals 2, okay, for our range interval right here. And now let's look at the upper end of our interval right here. So I'm going to trace that horizontal line up, further up, and further up. Okay, and now it hits to y equals 5, and the graph is still hitting, the graph in red is still meeting with that black dotted line right there. So in that way, that means y equals 5 is also included, okay, is also accepted as a part of the range right here, as being an element, a member in the range, or as an output that can come out. Because see, right here in the picture, it looks like it's estimated that when x equals 3, when input equals 3, then we have an output being 5. That's what the line here is saying. Okay, see, in full view, when x equals 3, y equals 5. Okay, at least that's what we estimated. Okay, and so in that way, the range is concluded to be the interval, the closed interval from 2 to 5. This is saying from 2 to 5, y equals 2 to 4, y equals 5. Okay, and that's the answer to our range of this problem here in particular. All right, and so now let me bring in another problem for this particular example, and we should be good with example 2 right here. All right. And so now what about part E of this example, where now I'm going to bring up another graph. All right, so here we go. This is the graph for whatever function that is. Okay, knowing the rule or not knowing the rule, that's okay. Okay, but there has to be a rule. That's why it consequently ended up with being a graph right here. But now for this graph, let's identify from this graph the range of our function. The function that's represented by this graph right here. Okay, so again, I'm going to put it in full screen view, and I'm going to use a horizontal line to detect. So right now, initially my horizontal line at y equals -1. It did not. Right now it's not crossing with the graph at all. Okay, so down here is not possible. It's not possible. And now I'm going to bring it up a little bit. Okay, now slightly below 0, it still did not cross with any bit of the graph at all. Okay, but now we're going to start moving it up. So now anywhere above 0. See, now when my line here, my horizontal line stays anywhere above 0. See, y equals 0 is right here and above that. Okay, so right here y equals 0, and now above that. Okay, so now it looks like anywhere above 0. Anywhere above 0. So now I can have some conclusion already. The range, it looks like the range for this function, for this graph, is anywhere between 0 and positive infinity, because that's how we indicate as interval notation, being above 0. Okay, and now let's further look into the graph. Okay, so now I'm going to really zoom it out. So it doesn't look like there will be anything that stops this graph from growing up vertically. Okay, again, in my word, I'm saying that it doesn't look like there's anything that stops this red graph from rising up vertically or growing up vertically, because the proof is right here. Obviously, as I keep rising up my horizontal line, see right now it seems like it's not crossing, but it will at some other points later. Okay, outside of our usual viewing window, or at a far out zoom right here, it does cross. Okay, the black line is still crossing with our graph right there. All right, so now in this case, apparently it is clear, it is evidently that the range has to be anywhere between 0 and positive infinity. That's why I'm having this. But now, so this is not an and, so we have to put, this is not an and where we can include. That's what I meant earlier. That's what I meant to try to say earlier. So we have to use parentheses here. But what about 0? Does our graph hit down to as low as y equals 0? Indeed, yes. Okay, now in full view again. All right, so let's bring it all the way down to 0. Okay, in closer zoom, when x equals 0, okay, it looks like we estimated that it looks like the graph does hit down to the y equals 0 here. Okay, so in the way how we see in this graph right here, then yes, we do include y equals 0. So the range for this graph here is anywhere from 0 and up, Okay. All right, so that's the end of this particular example right there. And so I brought up the toolkit functions, a couple of the toolkit functions earlier to investigate and explore the domains. And now I can bring up a couple of toolkit functions again. Okay, for us to this time explore from the graph of these toolkit functions. We're going to explore the range. Okay, so let's start out with our f of x equals x. Okay, and I also discovered the domain for this toolkit function from the graph in the earlier part of the video lecture here. Okay, but now this time let's try to identify domain. Let's try to identify the range here. We already knew the domain of this toolkit function is anywhere from -infinity to infinity. Okay, and then this is called an identity function, whatever that is. Okay, and so now, all right, so here it is. This is the graph for this particular identity function right there. And so it has already been agreed, right? It was already agreed that the domain for this toolkit function is vertically, from the graph, horizontally anywhere from -infinity to infinity, the horizontal spread of that. But we're done talking about that at this point right here. Okay, and so now let's look for the range. Okay, let's look for the range for this toolkit function. And so now when you're looking at the graph, when you're trying to identify, for this function you also know the rule and you see the graph right here in front of you. You know the rule and you see the graph. So let's use both interchangeably, okay, and flexibly to identify the range, the vertical spread of our graph like that. Okay, so right here, it looks like, okay, the vertical spread here is anywhere from -infinity to infinity right here, -infinity to infinity. Okay, because you see, all right, and now I had the horizontal line put up right here. So using this horizontal line, at least to me, it's the best way to detect the vertical spread. So now I'm going to keep bringing the line up and up and up, and it doesn't look like it's going to stop crossing. Okay, I'll keep dragging the viewing window down so that we can see more of what's above that, and no matter how high we put the horizontal line, it's still crossing with the graph at some point. Okay, and now how about let's bring it down low. Okay, I'm going to bring it down, okay, to the negative side. And so once again, we're still seeing the horizontal line is still crossing with the graph. And I'm going to bring it down further, down lower, and lower. Now it's outside of the viewing window. I'm going to drag that up, okay, to see more. And it's still crossing, okay. And so now we are ready to make that conclusion. Apparently the range for this, in the way we're looking at and with what we're understanding, then the range for this identity function has to be, so the domain is anywhere from between, -infinity to infinity. So the range is another interval, but vertically from -infinity to infinity. Okay, because you see vertically it goes 0 is here, it goes all the way up, okay, and it also goes all the way down. -infinity down here and +infinity down up that way. Okay, and that's the idea. All right, so for this particular identity function, we're done right there. Okay. And now let me bring up another toolkit function, or a couple other ones right here. All right, so I introduced this one right before, and when I was still introducing about the range right here. So let's look at that again. All right, so how about our function here is that famous simple quadratic function. We already knew that the domain of this function was anywhere from -infinity to infinity. We knew that from our earlier discussion. Okay, but now let's find out what the range of this function is. Okay, and once again, this is why it's saying, you know, the range is a set of possible output values of a function. Okay, and so this is our graph right here. This is our graph for this simple quadratic function. It has the graph as given here. Okay, so now let's look at the graph, but now keep in mind our goal is to identify the vertical spread, the vertical, how high up, vertically up the graph can reach, and how low vertically down the graph can reach. Okay, and so the best way to judge that is to use a horizontal line, okay, to detect. Okay, so right now it looks like, see, if we're anywhere between 0, anywhere above 0, anywhere above the x-axis, that's where it's y value greater than 0. Okay, we've seen this before when I was introducing this, and now we're reinforcing that understanding, re-emphasizing that understanding. Okay, so anywhere y greater than 0, okay, that's why the horizontal line is still crossing through the graph right here. See, anywhere we place the line, for this kind of graph, it crosses at 2 points, but see, as long as we have a crossing, horizontal line cross through the graph, we're good, and say, hey, that line is in the range of the function. And so now it looks like we're looking at anywhere 0 to positive infinity. Okay, and of course we have to use parentheses for this, but then what about 0? Does this graph reach down as low as 0? Yes. For this specific function, f of x equals x squared, we do have an input that makes the graph hits to as low as 0. When x equals 0, 0 squared equals 0. So the y value equals 0 is another possible output value. So we do accept 0. Okay, and graphically that's what it says right there. It stays anywhere right on the x-axis and being above that. Okay, and so this is the range of this function. Now formally concluded here. All right, and so now let's look at another one. All right, so let's look at another one. So let's look at this, the following toolkit function right here. How about f of x equals 1 over x? Okay, and we also investigated the domain of this function, of this toolkit function, when we were still looking at domains earlier. Okay, and so now we already knew from our earlier part of this lecture that the domain of this toolkit function is anywhere from negative infinity, between negative infinity and 0. That's one zone right here. And then union with anywhere between 0 and positive infinity. Okay, so that's another separate zone. So two zones unions together. That's the entire domain of this function. So now what about the range? Okay, so what about the range? So now let me bring up the graph for this function right here. The graph here looks as following. All right, so this is the graph of our function. But then this time, so that same graph we have seen quite a few times up to this point. But now let's look at the vertical spread, okay? How high can this spread and how low can this spread? And is there, this function is a little special. That's why, you know, any time I'm teaching a college algebra class, this function has to be brought in and discussed about. Okay, let me now show the horizontal line. Okay, and right here where I originally placed the horizontal line, it's already shows something right here. See, this horizontal line y equals 0, or the x-axis itself. Right here at that value y equals 0 vertically, do we have a value for x that makes the outputs equal 0? Nope, we can't. Okay, see, search throughout the whole graph right here, left and right. Do we have a satisfying, can we find a satisfying x values that give the output equal 0? Or is there anywhere here that the graph touches that line y equals 0? As a matter of fact, it looks pretty close here, right? Well, that's just because even machine is failing to show the difference. But now when I zoom in close enough, it's still showing some difference. The graph in red will never cross that x-axis here. Okay, that graph in red, because and when I was introducing this back to our discussion about the basic graph for these toolkits function, I was using that term that this function is asymptotic. Okay, it has a horizontal asymptote, and the x-axis itself is the horizontal asymptote for this graph. So in that way, now I'm going to bring it up above y equals 0, and it does cross. It will cross. Okay, and crossing means, see, at some part the red graph stays above the black line, but then at some other part it switched down below. That means there has to be a crossing point somewhere. Okay, now let me bring it in really close look right here, full view looks, so that anyone can see some difference. See, there's a cross where the horizontal line is crossing with that red curve right there. You see the switch that the red is above black, but now here is red is below black right there. Okay, so anywhere above 0, then the graph does cross our horizontal line, and continuing to go further up and further up, the graph crosses it anywhere. And now once again back down to y equals 0, right here at that spot on the y-axis, right there on that spot on the y-axis, then the graph doesn't cross the horizontal dotted line at all. Okay, but now as I bring my horizontal line below 0, then it's crossing again. It's crossing anywhere below 0, it's crossing again. The crossing keeps happening for any value below, any of the values below 0. Okay, so now in that way, it is clear about the range here. Two separate zones again. Because the idea is we just won't have any value for y equals 0. So any y value is possible to create. Okay, for any y value we can pick a value from the domain to create any a y value other than 0, but we just can't find an input that gives the y equals 0. So that's why the range here is any y values other than 0. But that's the logic. So now putting that in interval notation. See, I saw two zones vertically from negative infinity to 0. Between negative infinity and 0, that's one zone right there. See, it's still on the graph. And then vertically, there's another zone between 0 and positive infinity. Okay, and these two zones, the separate intervals are union together. Okay, now that's our formal range of this function. Okay, the formally concluded as the range of this function, the reciprocal function here. All right, and so now another quick one that I want to mention, and then any other toolkits function that I could not point out, that I could not cover in this video lecture right here, then you can explore that. I intend to leave that for my students or my public viewers to explore them on your own right there. Okay, so let's look at another one right here. So what about f of x equals square root of x right here? Okay, so for this function, we already knew that the domain is anywhere from 0 to positive infinity. We learned this earlier. Okay, and this is the graph. All right, so this is the graph of our square root function, and we have seen this quite a few times. And so, I also discussed about this earlier, so there's no need to talk too much about that. Okay, but in this domain right here, we had we have seen this graph earlier, but I did not say what rule that was. So now we're seeing that same exact graph again. So yes, the one I brought up earlier was the graph for this toolkit function, the simple square root function. And we know that the domain here is from 0 to positive infinity. So let's look at the range here. Okay. And earlier when we saw this graph, we only beat around the bush. But now, okay, with this graph right here, with my horizontal line right there, okay. All right, so let's bring in my horizontal line. All right, so now as I'm moving my horizontal line, see, anywhere starting at 0, the graph will start hitting. See, so for this graph, we know the specific rule. So we know that when input equals 0, x equals 0, we do have an output down to as low as square root of 0, which is equals 0. So the output vertically, so the graph here, even though it does not show solid point, but the graph does reach down to as low as y equals 0 vertically. Okay, and then from there on, as we keep dragging up that horizontal line right there, then the line will keep meeting with the graph. The line will keep meeting with the graph, no matter how high we're dragging it. Okay, and maybe it appears to be not crossing. That's because our viewing windows was limiting it, was restricting our view, but it's still crossing outside of that window. Okay, in case the window was not showing. All right, so in the end, now it is clear that for this graph right here, for this toolkit function with the graph that you are currently seeing, the range now has to be vertically anywhere from 0 and up, from 0 and up, and that's the range of this function. All right.